a quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. This record surveys ideas people have proposed for moving a craft between stars, from near-term engineering to far-future physics. It explains what we can do today with rockets, what we can plausibly build with nuclear energy, and what might be possible if we solve major problems in materials, power, and long-duration life support. It also covers concepts that are mostly math or speculation, including warp drives, wormholes, and claims of recovered craft, and it states clearly what would have to be true for those claims to become real propulsion. Throughout, the focus is on constraints, energy, mass, heat, and time, because interstellar travel is mostly a problem of numbers. The goal is not to promise a miracle, but to describe the landscape of ideas in a calm, documentary way, so the listener can sense what is solid, what is uncertain, and what is still imaginary. Tonight, we go through advanced propulsion systems for interstellar travel. Somewhere in a vault, someone once filed a note that sounded almost like a bedtime story. It said that if you want to cross the gap between stars, you must first learn to respect the gap. In our everyday lives, space looks like a place you can drift through, a quiet black ocean. In reality, it is a vast distance problem. Even the nearest star system is so far that a normal rocket, the kind we use to reach orbit, would take tens of thousands of years to arrive. That is not a trip. It is a geological process. So the archive starts where the numbers start. To go fast, you need energy. To keep going, you need reaction mass, or some way to push against something else. To arrive in one piece, you need shielding, cooling, navigation, and patience. And to tell the truth about any propulsion idea, you need to ask a simple question in plain language. What is being pushed? What is doing the pushing? And where does the energy come from? Most people first learn about rockets as fire that pushes a vehicle forward. That picture is accurate. A rocket works by throwing mass out the back at high speed. The vehicle moves forward because momentum is conserved. The deep lesson is that the fuel is also the propellant. The stuff you burn is also the stuff you throw away. This makes rockets powerful, but it makes them heavy. If you want high speed, you usually want high exhaust velocity. High exhaust velocity often means high temperature, high power, and difficult materials. The rocket equation is the quiet judge that sits behind every design. If you want more speed, you need more propellant, and that extra propellant makes the craft heavier, which then demands more propellant. It is not impossible, but it is relentless. Chemical rockets are the champions of quick bursts and strong thrust. They can lift from a planet, they can escape gravity wells, and they can push a spacecraft to the outer solar system. But their exhaust velocity is limited by chemistry, by how much energy molecules can release when bonds rearrange. That is enough for orbit and for many planetary missions. It is not enough for deep interstellar flight at a time scale that fits a human life. When people talk about interstellar travel, they often mean speeds like a few percent of the speed of light. Maybe 5%, maybe 10, maybe more. At 1% of light speed, the nearest stars are still decades away. But at least the trip can fit inside a lifetime if you plan carefully. At 10%, you start talking about a few decades, including acceleration and braking. Beyond that, the physics becomes more severe, not only because of energy, But because the interstellar medium becomes a dangerous spray of dust and atoms that hit like bullets, the archive notes something that surprises beginners. You do not just need to accelerate. If you want to actually arrive at a target star and do science there, you need to slow down. That means you need to pay the propulsion cost twice. You need one budget for getting up to speed and another budget for stopping, unless you use some external braking method like a sail that can push against the destination star. A simple bridge between chemical rockets and more exotic systems is electric propulsion. In electric thrusters, you use electrical energy to accelerate propellant to a much higher exhaust velocity than chemical engines can manage. Ion engines and Hall effect thrusters are the best known. They sip propellant, often xenon, and they produce a small but steady thrust. Over months or years, they can change a spacecraft trajectory dramatically. They are not great for launching from Earth because their thrust is low, but they are efficient in space. For interstellar travel, electric propulsion teaches a valuable idea. You can separate the energy source from the propellant. You might have solar panels near the sun, or a nuclear reactor, or beamed power, and you use that energy to accelerate propellant. That means you can choose a propellant that is easy to store, and you can choose an energy source that is not bound to chemical reactions. If you scale electric propulsion to higher power, you run into heat. Every watt you generate ends up as heat that must be rejected by radiators. In space, you cannot dump heat into air. You can only radiate it away as infrared light. Radiators become large and fragile. At interstellar scales, radiators become a major part of the design story. Some concepts aim to increase thrust while keeping reasonable efficiency. There are magnetoplasma engines like VSIMR, which use radio waves to heat a plasma and magnetic fields to direct it. The idea is to vary exhaust velocity and thrust based on the mission phase. In principle, it can give high performance, but it requires very high electrical power and careful thermal management. It is a reminder that in space travel, power systems are often the real engine. Nuclear energy is the next major step. Nuclear reactions release far more energy per unit mass than chemical reactions. A nuclear thermal rocket uses a nuclear reactor to heat hydrogen, then expels it through a nozzle. Because hydrogen is light, you can achieve higher exhaust velocity than chemical engines. Nuclear thermal propulsion has been tested on Earth in programs like NERVA. It is not fantasy. The challenges are political, safety-related, and engineering-related. You must manage radioactive materials, you must prevent contamination, and you must build a system that is reliable. Nuclear thermal rockets could enable faster travel inside the solar system. They could cut travel time to Mars and beyond. But for interstellar travel, even nuclear thermal is still not enough unless you accept trips that last centuries. Still, it matters, because it shows that some advanced propulsion is simply a choice to use higher energy reactions that we already understand. Nuclear electric propulsion is another variant. Instead of heating propellant directly, a reactor generates electricity which powers electric thrusters. This can be efficient and flexible. Again, the limiting factors are power density, heat rejection, and reactor mass. At large scales, you may need megawatts or gigawatts of power for meaningful interstellar performance. Then there is nuclear pulse propulsion, most famously associated with Project Orion. In that concept, You detonate nuclear bombs behind a spacecraft and ride the shock on a massive pusher plate with shock absorbers. It sounds wild, but it is based on known physics. It can, in principle, produce high thrust and high specific impulse, enough for rapid travel in the solar system and perhaps for faster interstellar precursors. It is also a concept that collides with the reality of nuclear treaties, ethics, and the risk of fallout if used near Earth. The archive treats Orion with a certain sobriety. It is not a magical drive. It is an extreme engineering solution using a known energy source. It would require precise bomb manufacturing, reliable shock absorption, and a pusher plate that can survive repeated blasts. It would also require accepting the idea of using many nuclear devices for a single mission. In a world that already struggles with nuclear safety, that is a hard sell. Yet as a physical method, it is one of the more plausible, high-performance systems, which is why it keeps returning in discussions. A quieter cousin of Orion is the idea of pulsed fission or pulsed fusion microexplosions, perhaps using laser or magnetic compression, but on a smaller scale with less political baggage than full nuclear bombs. You can imagine a craft that feeds tiny pellets into a reaction chamber, ignites them, and directs the plasma out a magnetic nozzle. This is the boundary between rocket and power plant. Fusion propulsion sits at the heart of many interstellar dreams. Fusion combines light nuclei to release energy. It is the process that powers stars. If we could control fusion reliably and efficiently in a spacecraft, we would have a very high energy density system. There are many ways to attempt fusion. Magnetic confinement, like tokamaks and stellarators, uses strong magnetic fields to hold hot plasma. Inertial confinement uses lasers or particle beams to compress a fuel pellet. There are also more exotic approaches like magnetized target fusion and field-reversed configurations. The important documentary point is that fusion on Earth has been difficult. There have been impressive advances, including brief ignition events in laboratories, but turning that into a compact, reliable, long-duration engine is still beyond what we can do. However, interstellar studies often assume that fusion will mature because the physical principles are known, and because fusion offers a path to high exhaust velocity without needing antimatter. Classic interstellar designs like Project Daedalus and later Project Icarus used pulsed fusion, often deuterium and helium-3, with pellets ignited by electron beams or lasers. The craft would be huge, more like a flying factory than a sleek ship. It would carry thousands of tons of fuel. It would not be a crewed ship in most designs. It would be a probe that flies past a target star at high speed and sends back data. These studies are important because they connect propulsion to the full system. They include power, communications, shielding, and mission design. They show that even with fusion, interstellar travel is an industrial-scale project. It is not just an engine swap. A crewed fusion ship raises more questions. How do you protect people from radiation, both from the reactor and from cosmic rays and interstellar dust impacts? How do you provide gravity, food, air, and psychological health over decades? Propulsion is only one part, yet propulsion sets the schedule, and the schedule shapes everything else. Antimatter propulsion is the next step up in energy density. When antimatter meets matter, they annihilate and convert mass to energy. The energy per kilogram is enormous. With enough antimatter, you could, in theory, power very high-performance rockets or produce intense photon thrust. The problem is that antimatter is extremely hard to produce in large quantities, extremely expensive in energy terms, and extremely hard to store. You need electromagnetic traps and very high vacuum. You must prevent contact with ordinary matter. Even small storage failures would be catastrophic. In the archive, antimatter is treated as both a tantalizing idea and a warning. It is not a free lunch. If you produce antimatter with particle accelerators, you spend far more energy than you get back. You might justify it if you have a massive solar power economy in space, or if you can collect naturally occurring antimatter, like some theories suggest might exist in tiny amounts trapped in planetary magnetic fields. But for now, antimatter remains far from practical. Yet antimatter might still play a role as a catalyst. Some concepts use tiny amounts of antimatter to trigger fusion reactions, acting like an igniter. This could reduce the size of the ignition system and make fusion propulsion more feasible. Even then, you need antimatter production and handling, but in smaller quantities. There is also the pure photon rocket, the ultimate limit in a way. If you emit light in one direction, you get thrust in the opposite direction. Light carries momentum. A perfect photon rocket would have the highest possible exhaust velocity, because its exhaust is moving at the speed of light. But the thrust per watt is tiny. To get significant thrust, you need absurd power, and you must deal with the heat. A photon rocket is a reminder that even perfect exhaust velocity does not solve the power problem. Some of the most serious near-term interstellar proposals avoid carrying fuel at all. Instead, they use sails pushed by light or particle beams. A light sail is a large, thin, reflective sheet. Photons bounce off it and transfer momentum. In the solar system, a solar sail can use sunlight for gentle, continuous acceleration. This can be done with current materials for small probes. For interstellar travel, the big idea is to use a powerful laser array near Earth or near the Sun to push a small sail to a significant fraction of light speed. This is the heart of initiatives like Breakthrough Starshot. The probe would be tiny, grams to kilograms, with a thin sail. It might reach a nearby star in a few decades, then fly through the system quickly and send data back. The documentary truth is that this trades one hard problem for another. Instead of building an enormous engine in the spacecraft, you build an enormous infrastructure at home. You need a laser array with extreme power and precise beam control. You need adaptive optics to keep the beam on the sail for minutes or hours. You need the sail to survive intense heating and acceleration. You need the probe electronics to survive radiation and to send a signal from light years away with almost no power. But the advantage is clear. If the probe does not carry fuel, it can be much lighter, and the rocket equation becomes less punishing. For small payloads, beaming energy from a fixed location might be the first realistic path to interstellar speeds. Beamed propulsion can use more than lasers. It can use microwaves. Microwaves spread more, so you need a larger transmitting aperture, but they can be generated efficiently and may be gentler on materials. There are also particle beam concepts, where you shoot a stream of charged particles at a sail or magnetic field structure. This could provide thrust, and it could also be used as a way to send momentum and energy across long distances. A variation is the pellet beam or pellet stream. You throw a stream of small pellets out from the home system. The spacecraft catches them with a magnetic or physical system, using their momentum to accelerate. The craft does not carry much propellant, it collects it on the way. This is conceptually similar to refueling stations, but the station is a continuous stream. The hard part is alignment over astronomical distances and the engineering of the catch mechanism. Then there are the concepts that try to use the interstellar medium itself as reaction mass. The Bussard ramjet is the famous example. It imagines a spacecraft with a huge magnetic scoop that collects hydrogen from space, compresses it, and uses it as fusion fuel to produce thrust. In theory, it could accelerate continuously and reach high speeds without carrying fuel. In practice, the interstellar medium is very thin. The density is low, and at high speeds, the drag from collecting particles can be severe. Also, fusing ordinary hydrogen is extremely difficult. Most fusion schemes use deuterium, which is rare, or helium-3, which is rarer. Some ramjet variants propose using collected hydrogen as reaction mass heated by onboard power, not necessarily as fusion fuel. Others propose a RAM, augmented interstellar rocket, where you carry fusion fuel but collect additional reaction mass to improve performance. The archive treats ramjets as an honest question. If magnetic fields can gather enough mass, and if fusion can be managed, then the concept might work. If not, it remains a useful thought experiment that teaches how hard it is to push against empty space. There is also the magnetic sail, or magsail, used not for acceleration but for braking. If a spacecraft carries a large loop that generates a magnetic field, it can interact with the charged particles of the solar wind or the interstellar medium. This can produce drag and slow the craft without expending propellant. At a destination star, a magsail could potentially break by interacting with the star's wind. The force is small, but over long times it might matter. Again, size and materials are the challenge. A related idea is the electric sail, which uses long charged tethers to repel solar wind protons, creating thrust. It has been studied for solar system propulsion. It is less explored for interstellar, but the same principle could apply in the right environment. All of these sail ideas introduce a shift in how we think about a spacecraft. Instead of a compact vehicle with an engine, you might have a large, delicate structure like a sheet or a web. The craft becomes a piece of space architecture. It must survive micrometeoroids, radiation, and long-term degradation. It must remain controllable. Another approach to interstellar travel is to accept long trip times and focus on durability. This is where generation ships appear in the archive. A generation ship is a habitat that travels slowly, perhaps at a fraction of a percent of light speed, and the people who arrive are not the people who left. It is not a propulsion solution, it is a social solution to propulsion limits, but it changes propulsion requirements. You might accept lower speed if you can build a stable community. The archive also lists suspended animation, cryogenic sleep, and digital mines as ways to reduce the burden of time. If you can put a crew into deep hibernation, you might accept a 100-year trip. If you can send mines as data and rebuild bodies at the destination, you might accept even longer. These are not propulsion methods, but they are relevant because propulsion is about travel time, and travel time is about human life. Now the record turns to a detail that sounds small but grows huge. At high speeds, space is not empty. There are atoms of hydrogen, there are dust grains, And there are cosmic rays. At 10% of light speed, a dust grain can hit with energy comparable to explosives. A spacecraft must have shielding, perhaps a thick forward bumper, perhaps a cloud of sacrificial material, perhaps electromagnetic fields to deflect charged particles. But dust is often neutral, and neutral dust is hard to deflect. One can imagine a craft that carries a forward plasma shield, continually emitting ionized gas ahead of itself to vaporize incoming dust, or a craft that uses lasers to detect and break up particles in front, or a craft that travels behind a leading shield, like a separate block of mass that takes the hits. All of these add mass and complexity. Propulsion is never alone. Navigation is also part of propulsion at interstellar distances. If you travel for decades, tiny errors in pointing become huge positional errors. You need star trackers, inertial sensors, and perhaps pulsar navigation. You need communication beams that can aim back at Earth across light years. If the craft is small, these requirements become extreme. So far, most of what we have described stays within known physics and known conservation laws. It is advanced engineering, but not a rewrite of reality. Then the archive begins to list the ideas that feel like they belong to science fiction. The reason to include them is not to claim they are real, but to show what people have imagined and what hurdles they face. One of the most famous far future ideas is the warp drive, often linked to the Alcubierre metric. In that solution to Einstein's equations, space in front of a ship is contracted and space behind it is expanded. The ship itself sits in a bubble and does not locally move faster than light, but the bubble can move relative to distant points. It is a clever mathematical idea. The documentary problem is that the original warp metric requires negative energy density, a kind of exotic matter that has not been shown to exist in the needed form and quantity. Quantum field theory allows small negative energy effects in certain situations, like the Casimir effect between closely spaced plates. But scaling that to a macroscopic warp bubble is beyond current knowledge. Also, warp solutions often have issues like enormous energy requirements, stability concerns, and potential radiation hazards. If a warp drive were possible, it might not look like a ship engine at all. It might be a field generator that manipulates space-time. It might require a ring of mass energy around the craft. It might require controlling vacuum energy. For it to become real, we would need new physics, or at least new engineering, that can create and shape negative energy, manage huge power flows, and keep the bubble stable. Another faster-than-light concept is the wormhole. A wormhole is like a tunnel between two distant points in space-time. In theory, a stable, traversable wormhole also requires exotic matter to keep it open. Even if such matter exists, building or finding a wormhole would be an astronomical challenge. It might be more like building a piece of cosmic infrastructure than like building a spacecraft. In a documentary frame, wormholes are less a propulsion method and more a question about the topology of space-time. If wormholes can exist naturally, a civilization might find one and use it like a gate. If they cannot exist stably, the idea remains a narrative tool. There are also ideas about manipulating gravity for propulsion. Gravity is a field that shapes motion. So if you could generate or control gravity, you might steer without propellant. In known physics, generating gravity requires mass energy. You cannot create a gravity field without having mass or energy that already has that gravitational influence. A spacecraft cannot just turn gravity on like a light. However, there are proposals that use gravitational assists, which are real and used today. A spacecraft can steal a tiny bit of momentum from a planet by flying past it. This is not free energy, it is a transfer. For interstellar travel, gravitational assists inside the solar system could help. One might use a close solar flyby, called an Oberth maneuver, firing an engine near the sun where you move fastest, gaining more kinetic energy for the same fuel. This could provide a boost for interstellar probes. A solar Oberth maneuver with a high-performance engine, perhaps nuclear thermal, or even a solid rocket stage, could send a probe out at high speed. It would not reach a nearby star quickly, but it could reach the outer heliosphere and beyond in a reasonable time, and it could be part of a staged approach. The archive also mentions black holes, not as threats, but as engines. A rotating black hole has energy in its spin. In theory, you could extract energy via the Penrose process, or via electromagnetic interactions in the ergosphere. There are also concepts of using a small artificial black hole as a power source. Stephen Hawking predicted that black holes emit radiation, Hawking radiation, and smaller black holes radiate more. An artificially created tiny black hole could be an intense energy source. The challenges are extreme. Creating a black hole of useful mass would require energies far beyond current capability. Containing it, feeding it, and using its radiation as thrust would be a monumental engineering project. Yet as a far future concept, it is appealing because it stays within known physics, at least in principle. A black hole starship would be a kind of ultimate reactor. Another concept is the use of stellar engines. Instead of moving a ship, you move a star, or you move an entire solar system. A Shkardov thruster is a hypothetical megastructure, a giant mirror that reflects a star's light asymmetrically, producing a small thrust on the star itself. Over millions of years, a civilization could steer its star. This is not a human-scale mission, but it shows how propulsion can be reframed as long-term energy management. On the more practical end, the archive returns to beamed sails and asks how to slow down at the destination. A laser-pushed sail is great at accelerating away from home, but braking is difficult because you cannot carry a big engine and you cannot rely on a home laser at the destination. One answer is to use a sail that can interact with the destination star's light, using photon pressure to brake. Another is to use a mag sail to brake in the star's wind. Another is to send two stages, one to act as a brake or to deploy a braking medium. There are imaginative ideas like a sail that flips and uses the cosmic background light, or that uses the interstellar medium itself as a brake. But braking remains a central challenge for small, fast probes. At this point, the archive makes a quiet point about scale. Interstellar travel can be approached in two broad ways. One is small and fast, like tiny probes pushed by huge external beams. The other is large and slow, like massive ships with internal power. Both have advantages, and both require technologies we do not fully have. The small, fast approach keeps the payload tiny. That means the craft cannot carry heavy shields, big antennas, or complex instruments. It must be minimal and robust. It must survive acceleration of thousands of G. It might be built like a microchip with a sail. The large internal power approach allows a crew, large instruments, redundancy, and the ability to brake and maneuver, but it demands vast fuel and power. It becomes a civilization-scale shipyard project. Now the record turns to the idea of using the sun itself as part of the propulsion system. There are proposals for using a close approach to the sun to heat propellant, like a solar thermal rocket. A mirror focuses sunlight into a chamber and heats hydrogen. This can provide decent performance without a nuclear reactor, but it requires large mirrors and it is limited to near the sun. There are also proposals for using the sun as a gravitational lens for communications. This is not propulsion, but it matters for interstellar missions. If you send a probe to around 550 astronomical units, beyond the orbit of Pluto by a lot, you can use the sun as a lens to amplify signals from distant stars. That could allow imaging of exoplanets. It is a long trip, but within solar system scale. Advanced propulsion inside the solar system could make such missions feasible. It shows that interstellar science does not always require interstellar travel. Some of the most promising propulsion advances in the near future are not exotic drives, but better power and better materials. If we can build lightweight, high-temperature reactors, better superconductors, stronger composites, and better radiation-hardened electronics, many advanced concepts become less impossible. Superconductors matter because many advanced propulsion ideas rely on magnetic fields. Fusion confinement, plasma nozzles, mag sails, and particle beam systems all benefit from strong magnets. If you can make superconductors that work at higher temperatures, you reduce cooling requirements and mass. Materials matter because engines are mostly about managing heat and stress. A nozzle that can survive higher temperatures can achieve higher exhaust velocity. A radiator that can operate at higher temperature can radiate more power per area. A sail that can handle higher laser intensity can accelerate faster. Now, the archive opens a folder labeled with a warning tone. It contains concepts that claim to violate known momentum conservation, sometimes called reactionless drives. These include ideas like the EM drive, where microwaves inside a cavity were claimed to produce thrust without propellant. There are also Mach effect drives linked to Woodward's work, which propose that transient mass fluctuations could produce thrust by interacting with distant matter through a kind of inertia manipulation. The documentary approach is careful. Many experiments claiming reactionless thrust have later been explained by measurement errors, thermal effects, electromagnetic interference, or interactions with the environment. Conservation of momentum is one of the most tested principles in physics. Violating it would require new physics. That does not mean it is impossible, but it means the burden of proof is extremely high. For any claim of a propellantless drive, the key question is what the drive is pushing against. If it is pushing against the quantum vacuum, then we need a theory of how momentum is exchanged with the vacuum, and how that does not violate global conservation laws. If it is pushing against the universe through inertia, then we need a testable model that predicts measurable effects. If the effect is real, it must show up consistently in controlled experiments and scale with power in a predictable way. Some people point to the Casimir effect, where vacuum fluctuations produce an attractive force between plates. They ask if vacuum energy can be engineered for thrust. In known physics, the Casimir force is real but tiny and typically conservative, meaning you do not get net work from a closed cycle without paying energy. To make a vacuum thruster, you would need a way to create asymmetry and extract momentum continuously. No accepted method exists. The archive also includes claims of so-called electrogravitics, lifters, and high-voltage devices that supposedly reduce weight. Many of these are explained by ion wind, which is a real phenomenon where ions push air and create lift. In vacuum, the effect disappears. That does not remove all interest in the topic, but it clarifies that many dramatic demos are atmospheric effects, not anti-gravity. Then there is a darker corner of the folder, full of rumors and classified stories. It includes accounts of unidentified aerial phenomena, claims of recovered vehicles, and claims of reverse-engineered propulsion. In a sober documentary frame, we can separate three things. There are observations of unknown objects with limited data. There are human stories and testimony. And there are physical claims about propulsion. If a recovered craft truly used a propulsion method far beyond ours, there would likely be measurable principles at play. It might use compact power sources, advanced field control, or materials we cannot fabricate. But without public technical data, these claims remain unverified. It is possible that some observations involve advanced human technology, sensor errors, misidentification, or rare natural phenomena. It is also possible that some involve something genuinely unknown. The archive does not decide. It simply notes what would be required for the strongest propulsion claims to be real. For example, if a craft can accelerate at thousands of G without crushing occupants, it would need either unmanned operation, extreme structural strength, or a way to manage inertia. If it can hover silently without propellant, it would need a field interaction with Earth, the atmosphere, or space-time itself. If it can move in ways that appear to ignore aerodynamic limits, it might be using control of the surrounding medium, like plasma or electromagnetic fields. Or it might be exploiting sensor blind spots. Each possibility implies different physics. If any of these claims are true, the path to interstellar propulsion would change. But the archive insists on a rule. Extraordinary claims require extraordinary evidence. In science and engineering, you build on reproducible results, not on rumor. Still, it can be useful to map the claims and ask what would be true if they were true, because that helps you see which scientific questions would matter. Now, to stay grounded again, the record returns to the big energy picture. To reach a fraction of light speed with a large mass, the kinetic energy is enormous. Even at 10% of light speed, the kinetic energy per kilogram is about 0.5% of mc squared, because kinetic energy is 1/2 mv squared at non-relativistic speeds, and at 0.1 c that becomes huge. For a ship of 1,000,000 kilograms, the energy is beyond what our current world generates in a year. This is why interstellar travel feels like it belongs to a future with large-scale space industry. If you could build massive solar collectors near the sun, perhaps in a Dyson swarm style, you could collect petawatts of power. With that, you could produce antimatter, power laser arrays, and run industrial processes. Interstellar propulsion becomes more plausible when you imagine a civilization that has moved much of its industry into space and uses the sun directly. In this future picture, a laser array for pushing sails is not absurd. It is an application of a mature space power grid. A fusion-powered shipyard could manufacture enormous structures. A network of beacons and navigational aids could exist between stars. Interstellar travel becomes an extension of infrastructure rather than a one-off stunt. But the archive also respects the near future. It asks what could be done with incremental advances. A nuclear electric spacecraft with a high-power reactor could send probes much faster into the outer solar system. A solar sail could send small payloads to the outer heliosphere. A close solar flyby with a high-performance stage could achieve high escape velocity. An interstellar precursor mission might aim not for another star, but for the interstellar medium just outside the heliosphere, to study it directly. Voyager has already crossed into interstellar space, but it is slow and old. New missions could do better. Then the record speaks about communication. Interstellar travel is not only about getting there, but about telling anyone what you found. A fast probe might fly past a target star in hours or days. It would need to capture data quickly and store it. Then it might spend years transmitting back with a tiny antenna. This demands extreme coding and perhaps using the destination star as a lens. Or it demands a relay network. Again, propulsion connects to system architecture. Now we step deeper into the technical heart, but still in simple words. Propulsion methods can be compared by a few qualities: how much thrust they can produce, how efficient they are in converting energy to momentum, which is linked to exhaust velocity, how massive the engine and power system are, how hard they are to cool, how complex and reliable they are over long time. Chemical rockets have high thrust and low efficiency for deep space. Electric thrusters have high efficiency and low thrust. Nuclear thermal sits between. Fusion aims for high efficiency and moderate to high thrust, depending on design. Antimatter offers extreme energy, but extreme difficulty. Beam sails move the power source off the ship. That changes mass, but adds a dependency on external infrastructure. Ramjet ideas move the propellant source off the ship. That adds dependence on the environment. Some propulsion methods also produce radiation hazards. Nuclear and fusion engines emit neutrons and gamma rays. You must shield the crew and sensitive electronics. Shielding adds mass, but shielding can be part of the ship's structure and water supply. Water is a decent radiation shield. Hydrogen-rich materials help. One can design a ship where the crew lives behind fuel tanks, using the fuel as shielding. For uncrewed probes, shielding can be lighter. You can accept more radiation, but electronics still degrade. Radiation hardening matters. Then there is the issue of propellant storage. Hydrogen is light but hard to store because it boils off. You can store it as a cryogenic liquid, but over decades, boil-off becomes a major issue unless you have active cooling. You can store it in chemical forms, like methane or ammonia, but that changes performance. Deuterium for fusion can be stored as a liquid. Helium-3 is tricky. Some studies imagine mining helium-3 from gas giant atmospheres. Others imagine producing it in reactors. In any case, fuel logistics become part of the civilization story. The archive also explains why acceleration matters. If you can accelerate at 1g, like Earth gravity, you can reach relativistic speeds in a year. That is the famous constant acceleration travel fantasy. But maintaining 1g for months requires huge thrust and huge power. It implies engines far beyond known capabilities, or a ship that is mostly fuel and power system. If you accelerate at a tiny fraction of g, like a sail pushed gently, you can still reach high speeds if you keep going long enough. This is why sails are interesting. They can provide continuous thrust, without carrying fuel. But the external power must be available. At interstellar distances, even small accelerations over years become meaningful. A millimeter per second squared seems tiny, but over a year it becomes about 30 kilometers per second. Over 10 years, 300 kilometers per second. Keep going, and you can get to a few percent of light speed. It is slow to start, but it accumulates. Now, the record addresses a subtle issue. If you go fast, your ship must survive not only impacts, but also its own waste heat and the cosmic microwave background. At high relativistic speeds, the cosmic background radiation becomes blue shifted in the forward direction, increasing its energy. At very high speed, it could become a radiation hazard. This is a far future concern, but it shows that the universe itself becomes different at high speed. Relativity also changes the energy accounting. As you approach light speed, additional acceleration requires ever more energy. The ship's kinetic energy grows without bound as speed approaches c. Time dilation can help the travelers, making the trip feel shorter to them, but it does not help the outside world waiting for a return. In a documentary tone, one can say that the speed of light is a hard limit for local motion. Getting close is possible in theory, but it becomes expensive. So where does that leave us? It leaves us with a layered map of possibilities. At the lowest layer, we have improvements to chemical rockets and in space refueling. This can make solar system travel routine. It can build the industrial base. At the next layer, we have nuclear thermal and nuclear electric systems that can move heavy payloads and shorten solar system timelines. These can enable large space construction. At the next layer, we have fusion propulsion, which could plausibly push probes and possibly crewed ships to nearby stars within a century, if the engineering matures. At the next layer, we have beamed propulsion for small craft, which might allow interstellar flybys within decades using infrastructure rather than onboard fuel. Then we have the speculative layer, warp drives, wormholes, artificial black holes, vacuum energy drives, and rumored field propulsion, which would require breakthroughs that we cannot currently predict. But the archive does not end there. It zooms in and tells stories of particular mission architectures, because propulsion is never only an engine. Imagine a fusion probe. It is assembled in orbit, far from Earth's atmosphere. Its fuel tanks are huge. It carries a cluster of fusion engines that fire in pulses. It accelerates for years. During this time, it points a thick shield forward. It occasionally makes tiny course corrections. Inside, its computers run checks. Its instruments sleep. It does not need a crew, so it can be small, but not too small, because it needs radiators and communication. As it gets close to its target star, it might not break. It might simply fly through at high speed. In the final days, it wakes up its cameras and spectrometers. It maps planets. It measures magnetic fields and stellar wind. It takes snapshots of any moons and rings. Then it passes by and begins the long task of sending the data home. Now imagine a beamed sail probe. It is built like a wafer, a thin chip with sensors and a transmitter. It is attached to a sail the size of a building, or larger. On launch day, a laser array on Earth or in orbit locks onto it. The sail begins to accelerate. Within minutes, it is moving faster than any human-made object. It leaves the solar system quickly. For years it coasts. As it approaches the destination, it cannot slow much. It might use its sail as a brake if it can interact with the destination star's light. but the light is weak compared to the pushing laser. It might slow only a little. It flies through the system in hours. It might send back a burst of data. It might be lost. Yet if many such probes are sent, even a small success rate could yield a rich picture. Imagine a crude fusion ship. It is not a sleek rocket. It is a long structure with rotating habitats for artificial gravity. It has thick shielding. It has a forward dust shield, perhaps a block of ice, or a shield of layered materials. It has a fusion reactor in the back, far from the crew. It has radiators that spread out like wings. It might carry a farm, water recycling, spare parts, and robots. The crew would live in a closed ecosystem. They would need not just propulsion, but a stable society. They would need governance, education, and conflict resolution. They would need medical capabilities. They would need the ability to repair almost anything. Over decades, the ship becomes a world. This is why some people prefer the idea of sending robots first. Robots do not need air. They can sleep. They can be built to tolerate radiation. They can be small. They can be sent in many copies. They can scout a destination before humans commit. The archive notes that there is another approach, often called a seed ship. You send an automated craft that carries the means to build infrastructure at the destination, perhaps using local resources. It might build habitats, power plants, and even new bodies if minds are transmitted later. This is again not an engine solution, but it changes the mission design. Now, the record returns to the physics of thrust and asks a question that sounds almost philosophical. Is it possible to travel between stars without expelling reaction mass, using only some kind of field coupling? If you obey conservation laws, you must exchange momentum with something. That something could be emitted radiation, like photons, or it could be the gravitational field. But in known physics, gravitational radiation is extremely weak to generate. It could be interaction with external fields, like solar wind, but those fade in interstellar space. So most realistic designs still involve expelling something or using external beams. In the archive, there is a section on light itself as both propulsion and hazard. A powerful laser array can push a sail, but it can also be used to slow a sail at the destination if there is a receiver there. This suggests a network. If you had laser stations around multiple stars, you could accelerate ships between them, like trains between cities. The first station is the hard part. Once you have two, travel becomes easier. This is sometimes called the bootstrap problem of interstellar infrastructure. How do you build the first station at another star if you cannot travel there easily? The answer might be small probes that carry self-replicating manufacturing, or it might be long-duration, slow missions, or it might be that we will not do it until we already have a deep space industrial base. The archive also discusses the idea of using the interstellar medium for power. A ship moving through the medium can scoop charged particles and use them in a magnetic generator, like a wind turbine. But the density is low. The power is small. It might be enough for some systems, not for propulsion. Now, to keep the narration calm, we slow down and look at a few propulsion ideas in more detail, but as a story rather than as an outline. There is the nuclear salt-water rocket, a concept that uses a solution of fissile material in water, pumped into a chamber where it becomes critical, and fissions, heating the water to extreme temperatures and producing a very powerful exhaust. It is like a continuous nuclear explosion in a controlled flow. In theory, it could provide high thrust and high exhaust velocity. In practice, it is terrifying. The control problem is severe, the radiation is severe, and the risk of catastrophic failure is high. Yet it shows that fission can be used in more intense ways than a solid core reactor. There are gas core nuclear rockets, where the fission fuel is a hot gas contained by some method, allowing higher temperatures than solid core reactors. This could improve performance. The challenge is containing the gas, preventing it from mixing with the propellant, and managing radiation. There are also concepts like the fission fragment rocket, which aims to use the fragments of nuclear fission directly as exhaust, giving extremely high exhaust velocity. This could be very efficient for deep space. The challenge is capturing the fragments in a direction and building materials that can survive. In fusion, there are concepts like the fusion torch, a very powerful engine that can provide high thrust and high exhaust velocity, enabling fast travel and braking. This would require advanced fusion control and likely very high power handling. It is often treated as far future. Then there is the idea of using a magnetic nozzle to direct charge fusion products. This is important because many fusion reactions produce charged particles, which can be guided by magnetic fields, potentially converting fusion energy directly into directed exhaust without needing a traditional nozzle. But neutrons are a problem. Many fusion reactions produce neutrons, which are neutral and cannot be guided by magnetic fields. Neutrons carry energy away and make radiation. They heat the engine structure. They can damage materials. A fusion propulsion system must deal with neutron flux. This is why some interstellar studies prefer aneutronic fusion reactions, like proton-boron, which produce mostly charged particles. However, those reactions require higher temperatures and are harder to achieve. Again, the physics is known, but the engineering is hard. Antimatter also has variants. An antimatter thermal rocket would use antimatter to heat a propellant and expel it. An antimatter beamed core engine would direct charged particles from annihilation. There are also concepts of antimatter catalyzed microfission and microfusion. Each variant trades storage difficulty, thrust, and efficiency. Now the record mentions one of the simplest interstellar concepts, the world ship with a slow push. It might use a fission reactor and ion engines. It might use a solar sail for the first part, then coast. It might take thousands of years. But if you build a self-sustaining habitat, time becomes a less urgent problem. This idea is sometimes dismissed as too slow, but it is in a sense the most honest, because it does not require breakthroughs. It requires only the ability to build a stable world in space, which is itself a huge challenge, but perhaps less unknown than warp physics. In the background of all of this, the archive keeps returning to one idea, that propulsion is a way of spending energy to buy time. If you have more energy, you can travel faster. If you have less energy, you travel slower. If you cannot travel faster, you must change the mission to fit the time. This is why the conversation about interstellar travel often becomes a conversation about energy production. On Earth, energy production is limited by economics, environment, and infrastructure. In space, the sun offers enormous energy, but you must capture it. Nuclear offers compact energy, but it has risk and politics. Fusion could offer both, but it remains difficult. A future spacefaring civilization might build large solar arrays in close solar orbit, where sunlight is intense. It might beam power to spacecraft. It might build factories on the moon and asteroids. It might mine volatiles from comets. It might build habitats that provide labor and skills. In such a context, an interstellar mission is not a single rocket launch. It is the output of a mature economy. Now, there is another issue that the archive treats as a quiet plot twist. Even if you have a powerful engine, you may not want to push a whole ship to interstellar speed. You might instead push only information. That means sending messages, light, and probes, and building a kind of interstellar internet. Over time, you could build knowledge without moving people. This idea can feel disappointing to those who dream of starships, but it can also be seen as realistic. Our first steps beyond Earth were uncrewed. Our first steps to other planets were robots. It might be the same with stars. However, the archive also records the human drive to move, to touch, to live in new places. If the technology exists, people will likely attempt it. At this point, the narration turns to the question of propulsion for leaving and arriving at planets. Interstellar ships may not land. They may stay in space. Landing on a planet requires dealing with gravity and atmosphere. It might be easier to build habitats in orbit or on moons. A realistic interstellar mission might arrive and park in an outer orbit, then send smaller landers or drones. Or it might mine local asteroids and build a new infrastructure before any human lands. This reduces propulsion needs and risk. Now, the archive includes a section on the interstellar medium as a resource and a hazard. It is thin, but over long distances, you encounter a lot of it. If you had a large scoop, you could collect hydrogen for life support or for reaction mass. But at high speed, collecting it creates drag and heat. You must balance. There are also ideas for using the interstellar medium as shielding, by creating a bow shock of plasma in front of the ship. The ship could ionize the medium with a forward field and create a magnetic barrier. This is similar to how some planets create magnetospheres that deflect solar wind. But again, neutral dust remains a challenge. The archive also points out that the interstellar medium is not uniform. There are clouds and voids. A navigation plan might choose a route through lower density regions to reduce impacts. That requires mapping. Now we move into a calmer, more reflective tone, still documentary, as if a narrator is reading from a file. There is a habit in human history. When a technology is too difficult, people tell stories about it anyway. The stories do not prove the technology, but they can guide attention. Interstellar propulsion is one of those story-driven fields. It sits at the edge of what we can do, so it attracts both careful engineers and people who want to believe in shortcuts. The careful engineers often start from constraints. They ask about specific impulse, power to mass ratio, radiator temperature, neutron flux, material strength, and reliability. They run numbers. Their designs look huge and slow. The shortcut believers often start from desire. They imagine a drive that bends gravity or taps free energy. Their designs look small and fast. The archive tries to hold both in view without treating them as equal. It notes that engineering progress usually comes from constraint-driven work, but it also notes that theoretical physics has surprised us before. Quantum mechanics was once strange. Relativity was once strange. The existence of nuclear energy was once a mystery, yet these ideas were grounded in evidence and math. If there is a new propulsion breakthrough, it will likely come the same way, from theory that predicts real effects and experiments that reproduce them. So the record suggests a practical attitude: invest in what we can test, build better sensors, run better experiments, improve power systems, explore materials science. Keep an open mind, but do not bet a civilization on rumors. Now, the narration returns to specific speculative claims, but gently. There are stories of metamaterials, materials engineered at the microscale to bend electromagnetic waves in unusual ways. Metamaterials are real. They can create negative refractive index in certain frequency ranges. Some people have suggested using metamaterials to manipulate space-time or to reduce the energy needed for warp metrics. There have been papers exploring whether certain configurations could change vacuum energy distributions. At present, this is very theoretical. Metamaterials manipulate electromagnetic fields, not gravity directly. But because energy and momentum contribute to gravity, some people wonder if extreme field configurations could have gravitational effects. If any such effect exists, it is likely tiny under normal conditions. Scaling it up would be the challenge. There are also stories of high-temperature superconductors, enabling extremely strong magnetic fields in compact packages. That is more grounded. Strong fields can improve fusion confinement and plasma control. They can enable better mag sails. They can help with energy storage. Energy storage itself matters. A beamed sail might need onboard storage for communication bursts. A fusion ship might need buffers for pulsed power systems. Capacitors and flywheels, and perhaps superconducting magnetic energy storage could play roles. Now, as we travel through the archive, we find a note about propellantless drives that claim to use inertia itself. Inertia is the resistance to acceleration. In general relativity, inertia and gravity are linked. Some theories propose that inertia arises from interaction with the quantum vacuum or with the mass distribution of the universe, a concept sometimes associated with Mach's principle. If inertia has such an origin, perhaps it can be manipulated. This is where Mach effect thrusters are sometimes placed. The claim is that by rapidly changing energy in certain materials, you can create tiny transient mass changes and then create thrust by pushing on them. Experiments have reported small signals, but the field is controversial and not settled. A documentary record must say that even if small effects exist, scaling them to starship levels is unknown. Another family of claims involves gravitational waves. In principle, emitting gravitational waves carries momentum, so a device that emits asymmetric gravitational radiation could produce thrust. But generating meaningful gravitational waves requires moving huge masses at relativistic speeds. Our best detectors struggle to measure waves from colliding black holes billions of light years away. A small machine cannot easily emit strong gravitational waves, so as a practical propulsion method, it is not plausible with known tech. Still, the idea is a reminder that in physics, fields can carry momentum. Now, the archive turns to something that sounds mundane, but is crucial: reliability. An interstellar mission cannot rely on a repair crew from Earth. The craft must be self-maintaining. That implies redundancy, fault tolerance, and the ability to adapt to unexpected conditions. For a crewed ship, it implies the ability to manufacture spare parts from raw materials. perhaps using 3D printing and machining. It implies having robots for hazardous maintenance. It implies having a culture that values maintenance. For an uncrewed probe, it implies simplicity and hardening. Sometimes the best design is the one with fewer parts. Now, the record includes a section on propulsion as a staged system. Perhaps you do not need one engine type. You might use chemical rockets to reach orbit, then electric propulsion for deep space, then a nuclear stage for a high-energy burn, then a sail for long-term acceleration, then a mag sail for braking. This hybrid approach is often more realistic. A key idea in many studies is that leaving a planet is the hardest part with any low-thrust engine. So you might separate the launch vehicle from the interstellar vehicle. Build the interstellar craft in space. That reduces constraints. If you build the craft in space, you can use larger structures. You can use fragile radiators. You can use large sails. You can use materials that do not have to survive launch loads. So interstellar propulsion is connected to space manufacturing. Now, we pause on a thought that often appears in these records. The stars are far, but the solar system is already huge. If we master the solar system, we can build the base for interstellar, mining asteroids for metals, capturing comets for water, building habitats, building reactors, building lasers. Each step is a smaller version of the interstellar problem. In that sense, advanced propulsion for interstellar travel might begin as advanced propulsion for interplanetary travel. Now, the archive does not ignore the human element. It notes that interstellar travel is often imagined as exploration, but it can also be imagined as survival, as backup. If Earth faces long-term threats, a civilization might want off-world settlements. Interstellar travel is the farthest extension of that idea. But even without doom, curiosity is enough. Humans build telescopes to see distant worlds. At some point, someone may decide to send something there. Now the narration turns to one more class of propulsion that sits between sails and rockets, the concept of laser ablation propulsion. In this idea, a laser beam heats a material on the spacecraft or on a small pellet, causing it to ablate, to vaporize, producing thrust. The laser can be external. This allows a kind of laser-driven rocket. It is similar to sail pushing, but instead of relying on photon momentum, it uses the laser to create a jet of vapor. This can produce higher thrust for a given laser power, because the exhaust carries more momentum than photons alone. But it requires carrying ablation material or using external pellets. It also can damage the craft and requires precise control. There are also concepts like the light craft, where a laser heats air under a craft in the atmosphere to launch it. That is more about launch systems, but again, it shows how beamed energy can replace onboard fuel. For interstellar use, you could imagine a laser station that heats onboard propellant to extreme temperatures, producing a high exhaust velocity. This can be more efficient than a pure photon sail. Now the archive returns to the question of interstellar braking for fast probes, because it remains a central difficulty. One idea is to carry a magnetic loop that can deploy to a very large site. As the craft enters the stellar wind of the destination star, it uses the loop to generate drag. Another idea is to deploy a physical sail that interacts with light. Another is to fly close to the star and use its gravity and radiation to slow. But that is tricky. If you do not brake, you accept a flyby mission. That might be enough for first exploration. Now, as the narrator continues, we can feel the quiet repetition of the same theme. Every propulsion method has trade-offs. There is no perfect engine. A chemical engine is simple and powerful, but limited. An electric engine is efficient, but slow. A nuclear engine is powerful, but complex. A fusion engine is promising, but unproven at that scale. A sail is elegant, but needs infrastructure and has control challenges. A warp drive is a beautiful math idea, but demands exotic physics. A wormhole is a shortcut, but might not exist. So the archive asks, what should we do now, in the real present? One answer is to keep building better telescopes and better probes, to learn about exoplanets and interstellar space. Another is to invest in fusion, not only for propulsion, but for energy on Earth. Another is to build space industry and power infrastructure. Another is to run rigorous experiments on unusual propulsion claims with transparency and careful controls. Now, the record includes a story about how scientific fields mature. Early on, people throw many ideas at the wall. Most do not stick. Over time, a few become real. In propulsion, we have already seen this. Ion engines were once laboratory curiosities. Now they fly. Solar sails were once science fiction. Now they exist. Nuclear thermal was tested, then abandoned, and might return. So it is possible that some of today's fringe ideas will become tomorrow's standard tools. But the ones that will survive are the ones that can be tested and scaled. Now, the archive offers a calm explanation of why interstellar travel is so much harder than going to the moon. The moon is 3 days away. Mars is months away. Jupiter is years away with current methods. The nearest star is years away, even at light speed. And we cannot go at light speed. So interstellar travel is not a linear extension. It is a different category. Even if you could go 10 times faster than our current fastest probes, that is still far too slow. This is why advanced propulsion is not about improving by 10%. It is about improving by orders of magnitude. Now, the record includes a note on biological constraints. Humans need radiation protection. They need gravity, or they suffer bone and muscle loss. They need social contact. They need purpose. A decades-long voyage is a psychological challenge. Artificial gravity can be provided by rotation, but building a large rotating habitat is an engineering challenge. Radiation shielding adds mass. Closed-loop life support must be reliable. So again, propulsion is only part. Now the narration shifts to a discussion of the interstellar environment near a target star. There may be planets, asteroids, and dust. There may be a heliosphere, a bubble of stellar wind. A fast ship entering this region must navigate and avoid hazards. If the ship is moving very fast, it cannot easily dodge. It must rely on shielding. Some concepts propose sending a forward cloud of particles ahead of the craft to act as a shield, like a sacrificial mist. The craft replenishes this mist over time. It might be made of graphite dust or ice. It would absorb impacts and spread energy. But carrying shielding mass is costly. Now, the archive also considers the possibility of using the destination star's gravity for capture. If you arrive with a sail, you might use a close pass to change trajectory. But without braking, you cannot be captured. You will fly through. So for crewed missions, braking is essential. That means either carrying fuel to brake or relying on external infrastructure. This leads to another far future idea, the interstellar highway of beamed power. If you had a chain of stations between stars, you could accelerate and decelerate using beams. But building the first station is still the bootstrap problem. Now, the record returns to the idea of self-replicating probes, often called von Neumann probes. If you send a probe that can use local resources to build copies, it can spread infrastructure. If it can build a laser station at a new star, then you can later send larger craft and break. This idea raises ethical and safety concerns. Self-replication can be dangerous if not controlled. But as a concept, it solves the infrastructure problem. If one can build safe, limited replicators, the path to interstellar travel could be a gradual network building rather than a single leap. Now, the archive includes a note on how the meaning of interstellar travel changes if we consider long time scales. Over thousands of years, even slow ships can reach nearby stars. Over millions, a civilization could spread widely. In that sense, interstellar travel is not impossible. It is a question of patience and stability, but for human lifetimes, we want faster. So we return again to the engines that might do it. Fusion remains the central candidate. It is difficult, but it does not require exotic matter. It requires controlling plasma, managing heat, and building powerful magnets and lasers. These are hard, but they are in the realm of engineering. Beamed sails remain the central candidate for small payloads. They require building large laser arrays and strong sails. Again hard, but perhaps within a future of space-based industry. Antimatter remains a possible catalyst or far future fuel. It requires a space energy economy, and beyond that, warp and wormholes remain speculative. Now, the record zooms into the beamed sail story and tells it as a slow sequence. You build a laser array. It might be on the ground with adaptive optics, or it might be in orbit, or it might be on the moon. You choose a wavelength that the sail can reflect. You build phased array elements so you can steer the beam electronically. You solve the problem of coherence and phase control. You test it on small sails in space. Then you build the sail. It must be thin and light. It must have low absorption so it does not overheat. It must be strong enough to handle acceleration. It must be shaped so it stays stable in the beam. It might have a curved shape or a pattern of reflectivity that keeps it centered. Then you build the payload. It must be tiny. It must include sensors and a communication laser or radio. It must include a way to orient itself. It must survive acceleration. On launch day, you deploy the sail and point it. The beam hits. The sail accelerates. The craft leaves. Then comes the long, quiet coast. In that coast, the probe must survive radiation. It must manage its power, perhaps with a small radioisotope source or by harvesting light from the destination star as it approaches. It must keep its instruments functional. Finally, it reaches the target star. It has only hours to collect data. It takes images, spectra, measures particles, perhaps detects planets. Then it turns to transmit. Transmitting is another hard problem. A tiny probe has tiny power. It can send a narrow laser beam back, but it must point it precisely. Earth must have a receiving telescope. The signal is weak. The data rate is low, so you might accept that each probe returns only a small amount of data. But if you send many probes, you can build a picture. Now, the archive includes a note about the human tendency to focus on the engine and forget the receiver. Beamed sails require not only the laser, but the receiver network that can hear the whisper from a distant chip. Now, the record shifts to fusion again, but now with a more intimate view of what a fusion engine must do. A fusion engine must compress and heat fuel to extreme conditions. It must keep those conditions long enough for reactions to occur. It must direct the resulting energy into useful thrust. It must do this repeatedly for years. In pulsed fusion, you might ignite pellets thousands or millions of times. That is a lot of events. Each event must be controlled. The engine must not erode away. In continuous fusion, you must maintain a stable plasma. That is also hard. The engine must also be lightweight enough. A fusion reactor on Earth can be huge. For a ship, mass matters. So fusion propulsion demands high power density. That means intense fields and high temperature materials. This is why advanced materials are central. Now, in the archive, there is a note about the idea of using fusion, not only for propulsion, but for power, and using a separate method for thrust. For example, a fusion reactor could power a photon rocket, emitting a collimated beam of light, or it could power electric thrusters with very high power. But again, heat rejection is a problem. So some designs prefer to use the fusion products directly as exhaust. Now the record briefly mentions an unusual idea, the relativistic electron beam rocket. You accelerate electrons to near light speed and shoot them out the back. Because electrons are light, you need huge numbers and huge power, and beam spreading is an issue. But it is a pure electric rocket. Another idea is a neutrino rocket, emitting neutrinos for thrust. Neutrinos interact weakly, so they are hard to direct and produce. It is mostly a theoretical curiosity. Now the archive returns to black holes, because they are such a dramatic image, and it explains them calmly. If you had a tiny black hole with a mass of a mountain, it would have a Schwarzschild radius smaller than an atom. It would be incredibly dense. It would emit Hawking radiation if it is small enough. That radiation could be used as power. You could, in principle, feed the black hole with matter to keep it from evaporating and use its radiation for thrust, perhaps with a reflector or an absorber that heats propellant. But building this is beyond us. It requires energy beyond current capabilities and precision beyond current manufacturing. It also involves handling a dangerous object. If you lose control, it could fall through the ship or through a planet. So in the archive, black hole propulsion is a far future marker, a sign that in known physics, there are still energy sources that are extreme. Now, the record contains a quiet reflection on ethics. Some propulsion methods require massive energy and may have risks to the home world. For example, a giant laser array could be a weapon. A nuclear pulse drive involves many nuclear devices. Antimatter is dangerous, so any advanced propulsion program would need governance and trust. This is not a technical detail, but it is real. Now we return again to the rumor folder, because it keeps drawing attention. There are claims of craft that use gravity control, that can hover and accelerate without noise. Some claim that these craft use high-energy electromagnetic fields, perhaps spinning plasmas, perhaps superconducting rings. There are also claims about materials with unusual isotopic ratios. Without data, these are stories. But the archive suggests a way to engage with them responsibly. If someone claims a new propulsion effect, ask for a clear experimental setup. Ask for measurements in vacuum. Ask for independent replication. Ask for power in and thrust out. Ask for error analysis. Ask for scaling laws. If the effect is real, it will survive these tests. If it does not, it will fade. Now, the record makes a final pass through the known propulsion landscape and connects it to a vision of the future. Perhaps in the next decades, we will build better electric propulsion, and better nuclear reactors for space. That will make travel within the solar system cheaper and more common. We might build habitats on the Moon and Mars. We might mine asteroids. We might build large telescopes. Perhaps fusion will mature, first on Earth for energy, then in space for propulsion. Perhaps we will build a fusion-powered ship that can reach the outer solar system quickly. Perhaps we will build a fusion-driven interstellar probe. Perhaps at the same time, we will build laser arrays for moving cargo in space and for pushing sails. These arrays might start small, pushing small sails between Earth and Mars. Over time, they might grow. One day, a sail might leave the solar system and head for a nearby star. If it returns data, it will change how we see our neighborhood. If it does not, we will learn from the failure. Over longer time, if we build a space economy that can build giant structures, then larger interstellar craft become plausible. Perhaps a crewed mission will follow, and far beyond that, if physics allows, perhaps space-time engineering becomes possible. Perhaps warp bubbles or wormholes become more than equations. But the archive does not promise that. It only says that the universe is consistent, and our job is to learn its rules. Now, to keep the narration gentle, we imagine the ship not as metal, but as a commitment. A starship is a promise that someone will work on a project whose result they may not see. It is a promise that knowledge will be passed down. It is a promise that a civilization can hold focus. Advanced propulsion is therefore not only a technical field, it is a test of patience. Now the record adds a final set of practical notes, but still as a story. If you build a reactor in space, you must start it safely. You must manage shutdown. You must handle waste heat. You must protect the crew. If you build a sail, you must deploy it and keep it stable. You must survive micrometeoroids. You must manage charging and electrostatic effects. If you build a fusion engine, you must manage plasma instabilities. You must manage neutron damage. You must replace components. If you build a laser array, you must power it and cool it. You must coordinate many elements. You must prevent accidental beam strikes. If you build an antimatter system, you must trap particles and prevent contact. You must design fail-safe systems. In every case, the engineering is vast. Now the archive ends with the quietest statement of all. The gap between stars is real. The laws of physics are not personal. They do not care about our dreams, but they also do not forbid our dreams. They offer pathways, some steep, some long, some uncertain. A chemical rocket is a candle in the wind, strong enough to leave Earth. A nuclear engine is a furnace, strong enough to cross the solar system. A fusion engine is a star in a bottle, perhaps strong enough to reach another star. A sail is a wing catching light, perhaps strong enough to ride a beam into the dark. And beyond these, there are ideas that are still only sketches, warp bubbles drawn on paper, wormholes described in equations, rumors of craft that do not obey our expectations. For now, the honest path is to build what we can, test what we claim, and keep a clear eye on the numbers. The archive record closes slowly, as if a librarian is turning off lights. In the silence after the pages, one can almost hear the distant hum of engines that do not yet exist, and the softer sound of questions that will take generations to answer. This was a quiet archive story, where the story ends, sleep begins,